Okay, in this video, we want to consider cases that are exceptions to the octet rule. Now I'm going to present a couple cases. One thing I want to point out is that transition metals and lanthanides and actinides, they aren't well described by Lewis theory. We have to go to more advanced descriptions of chemical bonding to describe those very well. So they are certainly an exception, but the exceptions we're going to focus on here are cases where we can still use Lewis theory and draw Lewis structures, and we're dealing with main group elements, but that they can still have exceptions to the octet rule. So one case where we have exceptions to the octet rule are electron deficient molecules. So these are somewhat rare, but these are molecules where not all atoms have a complete octet. And boron is sort of notorious for this, at least right now in our study of chemistry. The electron deficient molecules that we're going to encounter would largely contain boron. So whenever you see boron, you kind of want to have in the back of your mind, this may not follow the octet rule. In an example, let's look at boron trifluoride. So boron is certainly less electronegative than fluorine. So the fluorines are going to be arranged around the boron. And when I look at my valence electrons, boron is going to give me 3. The 3 fluorines each contribute 7. So 3 times 7 is 21, plus a 3 from boron. I have 24 valence electrons. I've given out 2, 4, 6 in the single bonds, and so now we'll go 8, 10, 12, 14, 16, 18, 20, 22, 24. Alright, so I've given out all my valence electrons. And this is a scenario that we've not, or that's not that new to us, except in this case that boron is the central atom. And so we might say, just like with the nitrate ion, well, we'll just take one of the lone pairs from the fluorine and make a double bond between one of the fluorines and a boron. And so that seems perfectly reasonable. And so let's see what happens when we do that to the formal charges. So if we look at the formal charges on the right, if we consider the fluorines are all the same. They have 1 bond, 7 sticks. So the formal charges on all the fluorines are going to be the same in this case. Right, and so the formal charge, fluorine has 7 valence electrons, minus 6 balls and 1 6, so 7 minus 7. The formal charge on all these fluorines is 0. And if I look at the boron, right, the formal charge is going to be, boron has 3 valence electrons, no balls and 3 sticks, so 3 minus 3, the formal charge is 0 on the boron. So all the atoms have a 0 formal charge in the Lewis structure on the left. If we look on the right, these 2 fluorines didn't change, so their formal charge is still 0. But if we look at, I'll make this one green, if we look at that fluorine, fluorine has 7 valence electrons. Now it has 4 balls and 2 sticks, so 7 minus 6. The formal charge on that fluorine is positive 1. And if I look at the boron, we'll keep it blue. Now we have the 3 valence electrons, no balls, and 4 sticks. And so you can maybe see the problem. While the structure on the right, all the atoms have a complete octet, in that resonance structure, fluorine, the most electronegative element on the periodic table, has a positive formal charge. Right? Fluorine hates that. And the much less electronegative boron gets a -1 charge. And so BF3 would rather adopt this resonance structure even though the boron doesn't have a complete octet. And so boron is sort of notorious for this. It doesn't have to be fluorines. BCl3 does something similar. And so you may say, well, then how the heck do I know when a molecule is going to be willing to be electron deficient to give us better formal charges? And my answer right now is going to be when it's boron. So we want you to be aware that this happens, but it's fairly uncommon, and boron is fairly notorious for this. So most other molecules, if they don't contain boron, I'm not going to expect you to know that having the zero formal charges is better than having octets. But we do want to present this example so you realize that there are exceptions, this being one of them, to the octet rule. All right, another case, but basically falls into the category of electron deficient molecules, but in some cases it's easier because it's literally impossible to give everyone an octet. And that happens when we have an odd number of electrons. And so NO2 is an example of that. So nitrogen is going to be our central atom. It's less electronegative than the oxygens. When I count up my valence electrons, I get 5 from the nitrogen, 6 each from the oxygens. So 2 times 6 is 12, plus 5 is 17. And I think you're going to see when I give out electrons in pairs, it's not going to be possible to give everyone a complete octet. I've given out 4. Here's 6, 8, 10, 12, 14, 16. I only have 1 electron left. The oxygens are both full, so I put that on the nitrogen. Nitrogen only has 5 valence electrons, but the best I can do is take one of the lone pairs and make it a bonding pair. But even then, the best I can do is giving nitrogen 7 valence electrons. For second row atoms, I cannot exceed the octet rule, so I can't make another lone pair a bonding pair that would exceed the octet rule for nitrogen, so that's no good. And so this is literally the best that we can do. So when we have an odd number of electrons, we can't possibly give everyone a complete octet. Now, this being the best we can do doesn't mean that NO2 is very happy as a molecule. Whenever we have these odd numbers of electrons, and so we can't pair them all up, these are called radicals, or sometimes you hear them called free radicals. So this is fairly uncommon because these molecules are very unstable because they don't have all the electrons paired. They can't achieve an octet, but they're very important. They're involved in combustion chemistry. They're involved in neurotransmitters, immune response. They play a role in cell damage. So cancer, stroke, diabetes, Parkinson's, Alzheimer's have all been linked to radicals. Sometimes you'll hear people talk about antioxidants, vitamins A and C being some examples. Antioxidants are electron rich, and so they're good at eliminating radicals because they can give up electrons to the radicals to allow them to achieve octets and to get rid of this odd electron situation that they find themselves in. Okay. The last exception we're going to look at are expanded valence shells. And so some atoms, I say appear, but they do exceed the octet rule. This only happens for atoms in the third period or higher values of the n quantum number, right? Where 3 is the, when I say period 3, that's the principal quantum number 3. The reason that's important is because of the types of orbitals that are allowed depending on the principal quantum number, right? When n is equal to 1, we only have s orbitals. When n is equal to 2, we have s and p orbitals. And if all the s and p valence are filled, that's where the octet rule comes in, 8. But when n is equal to 3, now we have s, p, and d orbitals. So this is 100% true, but the explanation that we usually give when we're first introducing this is that what allows atoms in the third period or higher to go beyond the octet rule is that they have empty d orbitals that we can stick those electrons in that can participate in bonding. And so that's why central atoms in the third rule or higher are going to be able to exceed the octet rule. Another thing that plays a role in being able to expand the octet is just that they're bigger and we can fit more stuff around them. And so we'll look at a couple examples of this, of molecules that exceed the octet rule. And they all involve atoms in the third period or higher. All right, so our first example of an expanded octet is sulfur hexafluoride. So hexa is 6, So the formula for this compound is SF6. So we have the sulfur, and then, in fact, all 6 of the fluorines are coming off the one sulfur central atom. For our valence electrons, we have 6 fluorines. Each one of them has 7 valence electrons. So 6 times 7 is 42, plus the 4 from sulfur. 42 plus 6 is 48. And so I've already used, for the single bonds, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40, 42, 44, 46, 48. And so I've given out all of my valence electrons that I have to work with. All of the fluorines are happy. They all have complete octets. And then sulfur has exceeded the octet, but sulfur being in the third row of the periodic table, that is actually okay. We are allowed to expand the octet for sulfur. Those extra electrons, we can argue, are going into the unoccupied d orbitals. Okay, our next example is the phosphate ion. So phosphate is PO4 3-. Phosphor, being less electronegative than oxygen, will be the central atom. So we have P, O, 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 O. Our valence electrons, 4 oxygens, each of which have 6. So 4 times 6 is 24. Plus the 5 from phosphorus is 29. Plus the -3 charge gets us 32. So I've given out 2, 4, 6, 8 from the single bonds. So here's 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So I've given out all my valence electrons. All of the oxygens have a complete octet, and the phosphorus has a complete octet. So in this case, it kind of feels like, well, I'm done. But it's not the case. When n is equal to 3, so this 6th rule that we added to our guidelines for writing Lewis structures, check to see if by expanding the octets of any elements in the 3rd period or higher can improve the formal charges. And so let's see what the formal charges are currently in my molecule. So all the oxygens are the same. 6 balls, 1 stick. So for the oxygens, we have 6 minus 6 balls, 1 stick. So 6 minus 7 is -1. So all the oxygens have a -1 formal charge. And then the phosphorus, 5 valence electrons minus 4 balls and no sticks, it has a +1 formal charge. So when I add up all the formal charges, 4 -1s and a +1, I get -3, which is the charge on a phosphate ion, so that's good. But man, everything has a non-zero formal charge. Let's see what happens if I take one of the lone pairs on one of those oxygens and turn that into a double bond. That is going to give us, use a different color just for the heck of it, something that looks like this. All right, now the 3 oxygens with single bonds to the phosphorus, they didn't change. They still have 6 balls and 1 stick, so they're all still -1. But let's see what happens to the oxygen with the double bond and the phosphorus. So we'll make this one red. Its formal charge is going to be 6 minus 4 balls and 2 sticks. So the formal charge on that oxygen is 0. And for the phosphorus, we'll make it green. Phosphorus have 5 valence electrons, minus no balls and 5 sticks. And so the Lewis, or the resonance structure on the right, is the better resonance structure, because it has the smaller magnitude of formal charges. If I add up the magnitude of all the formal charges of the one on the left, I get 5. If I add up the magnitude of all the formal charges to the one on the right, I get 3. So 3 being lower than 5, this is the better resonance structure. And I can't help but have the magnitude of my formal charge is adding up to be 3 because phosphate has a -3 charge. And so you can see what happened when I made that double bond between the oxygen and the phosphorus became more negative. It went from +1 to 0. The oxygen went from -1 to 0, so it became less negative. If I try to make more multiple bonds with the phosphorus, that's going to put a negative charge on the phosphorus and zeros or positives on the oxygen, and we would rather the negative oxygens have the negative formal charges. So this is the best that we can do in the case of the phosphate ion. So when you have a central atom that's in the third row or the third period or higher, you need to check and see, can you draw a better resonance structure by expanding the octet, as we did in this case with phosphorus. All right, just one last example. We'll look at xenon tetrafluoride. So this may seem a little bit weird, involving a noble gas, but in the last 20-25 years, a small number of stable molecules involving noble gases have been discovered, including xenon tetrafluoride. And this is another example of a molecule with an expanded octet. So xenon tetrafluoride is going to be XeF4. So for our valence electrons, 4 times 7 for the fluorine is 28. Xenon has 8 valence electrons, so 28 plus 8, I have 36. So I have Xe, F, 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 F. I've given out 2, 4, 6, 8 with a single bond, so here's 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So I've given out 32. I have 36. All the fluorines are full, and so when this happens, any extra electrons we put as lone pairs on the central atom, because xenon is in the third row or third period or higher. It has those empty d orbitals that we can put electrons in, and so that's where the extra electrons will go. So I've given out 32. Here's 34 and 36. And so this would be the Lewis structure for xenon tetrafluoride. And I'm not going to do this in the interest of time, but if you want to convince yourself that the formal charges are good, I think you're going to find that all the fluorines and the xenon have a 0 formal charge in this molecule. And so that's likely the best that we can do in terms of the Lewis structure. Making multiple bonds isn't going to help us.